Welcome to this lecture of calculus. In this lecture, we shall study about the polar coordinates, and our main topic in polar coordinates will be to find the angle between the radius vector and the tangent vector of a given curve. But before starting our lecture to find out the angle between the radius vector and the tangent vector, since we are mainly dealing with the Cartesian form of the equation of the curves, so, so here our main or the first concern should be that how do we transform an equation from Cartesian form to its polar form. So we begin with an equation in a Cartesian form. So let f of xy equal to 0 be an equation of a curve. So we take this f of xy equal to 0 to be an equation of a curve. Then first of all we try to understand how this curve behaves in the xy plane. So suppose this is our coordinate system and we draw one curve here. Suppose this is a curve in the xy plane, then any point on this curve is represented by a coordinate x comma y. So we can represent the coordinates like this. Suppose if we have this point here, then its coordinates are usually given by x comma y. While we know this x is the distance of this point from the x-axis and y is the distance of this point from y-axis. So therefore, if we draw this perpendicular from this point on the x-axis, then this point, and similarly we draw a perpendicular from this point onto the y-axis, then this point is actually x and this point is actually y on the xy plane, and this point is the origin. Similarly, the other points are represented. Now if we convert this equation into the polar coordinates, we use a kind of a conversion, then this equation is converted into polar coordinates, and the polar coordinates are represented by r theta, and the equation is then given by and the equation is then given by this r is equal to phi of theta. Now first of all, here we try to understand what is this r and what is this theta. Now as we were representing here, we represented x as the distance of this point from the x-axis and y is the distance of this point from y-axis, and then this curve with the black color is drawn. Now if we draw a line from this point to the origin, which is 0 0, then this distance O, or we can call this point as P, then this distance OP is the distance of this point from the origin, which we denote by R. And then this vector OP, this forms an angle. That angle is actually known as theta. So actually what we are trying to say here is that whenever we have a point in the Cartesian form x comma y, that can always be represented by the combination of this distance of point P from the origin and the angle that it makes with the positive direction of x-axis. So if we have this point, we draw this point will induce an angle with the positive direction of x-axis. That angle is here denoted by theta. And this point P has distance r units from the origin, and the distance is denoted by r. So then these r and theta will uniquely represent every point in the Cartesian coordinate system. And then when we convert our given curve which is given in the form f of xy equal to 0 using this r theta, then the new equation so obtained, which is r as a function of theta, because when this theta changes, this radius vector will also change. This OP is actually known as the radius vector. So when we change this theta, when we suppose increase or decrease this theta, this tangent, this radius vector will go up and down and so on. So therefore this theta completely depends on r. And in fact, r inversely also depends on theta. So therefore every equation in the Cartesian form can be converted into the equation of the form r equal to phi of theta, by r is the distance of this point from the origin and theta is the angle that this vector, which we call the radius vector OP, makes with the positive direction of the x-axis. And there is one nice conversion rule for doing all this. The conversion rule is like this. Conversion rule is we use the substitution x is equal to r cos theta and y is equal to r sin theta. we do the same thing in every curve, then the curve is converted from f of xy equal to 0 or y equal to f of x into the system r is equal to function of theta, phi of theta. Here we shall also try to see how these conversion formulas are made. They are not actually chosen randomly, but they have a special meaning. If we look at this figure, which is OXP, suppose let's consider this as a right angle triangle, right angle at this point X, and theta is the angle which is between the side OX and OP. So in this right angle triangle OXP, OX is the base and OP is the hypotenuse, and similarly PX is the perpendicular, or we can call the height. Then if we look at this x divided by r, so we have this distance is x here. If we look at this x divided by r, this is actually equal to base divided by hypotenuse, and we know base divided by hypotenuse is actually equal to cos theta. So therefore this equation gives us x is equal to r cos theta. Similarly, we know this perpendicular y, it has the distance, or it has the length y, and we can write down this y divided by r, which is the hypotenuse. We can write this is perpendicular divided by hypotenuse, and we know perpendicular by hypotenuse in a right angle triangle is equal to sine of theta. So this equation gives us y is equal to r sine theta, and we can do exactly the same procedure for every point on this curve. Therefore, x equal to r cos theta, y equal to r sin theta. They are the meaningful and well-defined conversion formulas for converting an equation from Cartesian form into the polar form. Now let's come to our main topic of this lecture, which is actually finding the angle between the radius vector and the tangent. So our topic is finding angle between the radius vector and the tangent. Okay, now we shall try to understand this angle between the radius vector and the tangent vector using the figure. So we have, suppose this is our figure, and like this is the coordinate system, this is the perpendicular y-axis, and the horizontal line is the x-axis. And then we draw this is the tangent which touch the curve at suppose the point P, and assuming this P has now the polar coordinates r and theta. And then what we do, we connect it with this point of contact of tangent and the curve with the origin. So this is the line that connects this origin with the point of contact, and we know we call this OP as the radius vector, and this is denoted by r. And now this radius vector makes an angle theta with the positive direction of x-axis. Then our topic of concern here is to find the angle between the radius vector and the tangent. So OP is the radius vector, and this line on which we have a point T, suppose we call this tangent T here, then this TP is a tangent, and P is the point of contact of tangent and the vector, tangent and the curve. Then this tangent obviously makes one angle here, which is the angle between the radius vector denoted by OP and the tangent vector denoted by TP, and we call this angle always as phi. Now here we need to evaluate what is this phi for this given curve, which we usually denote by r is equal to suppose f of theta. So we shall here write down the rule as how do we evaluate this phi. Then our given curve is of the form r is equal to f of theta. So let r is equal to f of theta be given. Then the angle of intersection, then the angle between the radius vector and the tangent, radius vector and the tangent is given by as we denote this angle by phi. So this angle is given by tan phi is equal to r d theta by dr. So this is the formula for evaluating the angle between the radius vector and the tangent vector of the curve r is equal to f of theta. Now before going to take up examples, we shall write down one more formula here for evaluating the angle of intersection of two curves. So this is our like topic number 2, angle of intersection of two curves. Suppose we have two curves, let r is equal to f1 of theta and suppose r is equal to f2 of theta be two curves, then the angle of intersection between them is defined as, or we can say it is given by this alpha, which is equal to modulus of pi 1 minus pi 2. Now what is this pi 1 and pi 2 here? While pi 1 is the angle between the radius vector and tangent to the curve r is equal to f1 of theta. And on similar lines, pi 2 is the angle between the radius vector and the tangent vector of the curve r is equal to f2 theta. So what we need to evaluate the angle of intersection between two curves, we first need to evaluate the we first need to evaluate the angle between the radius vector and tangent vector of one curve r equal to f1 theta, and we shall denote the angle by phi 1, and then we compute the angle between the radius vector and tangent vector for the curve r equal to f2 theta, and we denote that angle by phi 2. Then the absolute difference between these two angles shall be denoted by alpha, and that alpha is defined as the angle of intersection of two curves. We will also try to understand it using an example here. So suppose this is the intersection of two curves, and they are also drawn in the suppose xy plane, and suppose this is the coordinate system, and then we draw the tangents to both of these curves at its point of contact where these two curves intersect to each other. So that point is the point of contact between these two curves, and we draw tangents to these two curves at this point of intersection. So this is our figure. Suppose we have this curve as suppose f1 and this curve as f2. Then for f1 we will make a tangent, we shall name it t1, and for the curve f2 we shall name the tangent as t2. Now first these two curves f1 and f2, they have, this is their point of intersection, which is the point P. At this point P we draw tangents to both of these curves. Now these tangents will also intersect among them. Then from this point P we draw a radius vector like this. Now if we look at this radius vector r, then this radius vector r forms an angle pi like this. We can call it pi 1, which is the angle between the tangent t1 and the radius vector r, which is actually the angle between the radius vector and the tangent to the curve r equals f1 of theta. Now this also makes an angle, this r also makes an angle with the tangent t2, which we shall denote like this, and this angle is now equal to phi 2. Then the absolute difference between this pi 1 and phi 2 is defined to be the angle of intersection between the two curves r equal to f1 of theta and r equal to f2 of theta. Now here we have one corollary. Two curves, suppose r is equal to f1 theta and r equal to f2 theta are orthogonal, or we can say orthogonal means perpendicular if this alpha is equal to pi by 2. That means if the angle between these two curves is equal to 90 degrees. Now here we shall try to draw a condition so that two curves are orthogonal. Now as our curves pi f1 of theta and f2 of theta are orthogonal, that means the angle between the radius vector and the tangent vectors will differ by a difference of pi by 2. That means we can write pi 1 is equal to pi 2 plus pi by 2. Or we can also write pi 2 equal to pi 1 plus pi by 2. Now if we apply tan here, so we can write this gives us tan pi 1 is equal to tan pi 2 plus pi by 2. And this equation gives us tan pi 1. Now we know that tan pi 2 plus tan plus pi by 2, that's actually minus cot phi 2. We can write this as, so therefore we have tan phi 1 is equal to minus 1 divided by tan phi 2. So now whatever is phi 1 and phi 2, we can clearly understand that the value of r d theta by dr for one curve will be the negative reciprocal of the value of r d theta by dr for the second curve. Hence, for orthogonal curves, the value of r d theta by dr for one curve is the negative reciprocal of value of r d theta by dr for the second curve. So we have to compute this r d theta by dr for both the curves, because we know that the angle between the radius vector and the tangent vector is given by r d theta by dr. And here, from the above observation, we have obtained that tan phi 1 for one curve is negative reciprocal of tan phi 2 for the another curve. So therefore, if we calculate r d theta by dr for one curve, then the other value must be the negative reciprocal of the same value, so that two curves are orthogonal. Now let's take a few examples to compute the angle between the radius vector and the tangent vector. So we have an exercise here. We need to find the angle between the radius vector and the tangent vector for these curves. The first one is r equal to a theta, then r square is equal to cos 2 theta, and third one is r equal to a into 1 plus cos theta. Now let's solve one by one. Let's take the solution of the first part. So we are given that, given r is equal to a theta. So we know that the angle between the radius vector and the tangent is given by tan phi is equal to r d theta by dr. So we shall first evaluate this d theta by dr and then substitute them in this formula. Now here r is equal to a theta. We differentiate both sides with respect to theta. We obtain, we will get dr by d theta is equal to a. So thus, what about this r d theta by dr? So therefore this is equal to r into 1 divided by dr by d theta. So this is now equal to r d theta by dr, and now our given r is equal to a theta, and we have to divide it with dr by d theta, and dr by d theta is equal to a. So therefore this is equal to theta. Now if we use this in this formula tan phi, so hence we have tan phi, which is equal to r dr d theta by dr, so therefore tan phi is equal to theta. So this implies this phi is equal to tan inverse theta. So therefore this is the angle between the radius vector and the tangent vector of given curve, given as part 1. Now similarly, let's take up the second part. So then here we are given that here r square is equal to a square cos 2 theta. And we need to find the angle between radius vector and tangent vector at theta equal to pi by 2. So then we know that angle between radius vector and tangent is given by tan phi is equal to r d theta by dr. Now again we shall differentiate the given equation with respect to theta. So now here r square is equal to a square cos 2 theta. So we differentiate both sides with respect to theta. We get on the left hand side 2r dr by d theta is equal to a square, a derivative of cos 2 theta, that is equal to minus sine 2 theta, and the derivative of 2 theta is equal to 2. So this implies this dr by d theta, this is equal to minus a square divided by r into sine 2 theta. Now we need to evaluate d theta by dr. So therefore, thus d theta by dr, which is the reciprocal of this thing. So this will be equal to minus r divided by a square sine 2 theta. So then r d theta by dr. We will multiply this equation both sides by r. We will get minus r square divided by a square sine 2 theta. Since we need to find the value of r d theta by dr, that's why we will multiply this equation both sides by r to obtain exactly r d theta by dr. Now this becomes, so now this is equal to, we know r square is equal to, r square was given, it was equal to a square cos 2 theta. So we can use that value here. So this is minus a square cos 2 theta divided by a square sine 2 theta. And now a square is cancelled, we get simply minus cot 2 theta. But we know that minus cot 2 theta, this is equal to tan 2 theta plus pi by 2. So therefore the value for r d theta by dr, that is equal to tan 2 theta plus pi by 2. So hence, by from the formula of angle between the radius vector and the tangent, it is given to tan phi. Now tan phi is equal to r d theta by dr, but that we have computed, it is equal to tan 2 theta plus pi by 2. Now cancelling tan on both sides, or we can see applying tan inverse on both sides. So this gives phi is equal to 2 theta plus pi by 2. Now our question second part was to find the angle of between the radius vector and the tangent vector at theta equal to pi by 6. So now we should substitute theta equal to pi by 6. Therefore at theta is equal to pi by 6, the angle between the radius vector and the tangent is equal to pi, which is equal to 2. Now substitute theta equal to pi by 6 here, so it's 2 into pi by 6 plus pi by 2, which you can clearly see this becomes pi by 3 plus pi by 2, and this can be computed to be equal to 5 pi by 6. So this is how we evaluate the angle between the radius vector and the tangent vector. Now third part will be left as an exercise. Now here we take one more exercise where we will show how the two curves are proved to be orthogonal to each other. So this shall be our example number 2. Show that the curves, one is r power n is equal to a power n sine n theta. Second one is r power n is equal to, suppose, b power n cos n theta intersect orthogonally. So we will show that these two curves intersect orthogonally. Let's take up their solution. So what we need to do, we will evaluate the angle between the radius vector and the tangent vector for both of these curves, and then evaluate the angle between their intersection, which is given by alpha equal to absolute difference of the angles. So let phi 1 and phi 2 denote the angles between the radius vector and tangent of the curves r power n is equal to a power n sin n theta and r power n is equal to b power n cos n theta respectively. So we are taking phi 1 to be the angle between the radius vector and tangent vector of the first curve, and phi 2 is the angle between the radius vector and tangent vector of the second. Now first let's evaluate phi 1. So for curve 1, for curve r power n is equal to a power n sin n theta we have. Now in order to take the derivative of this curve, we should apply log on both sides, which gives log r power n is equal to log of a power n into sin n theta. So this gives n log r is equal to log e power n plus log sin theta, or sin n theta actually. Now differentiating both sides, we obtain, now derivative of n log r will be equal to n by r into dr by d theta. Now log e power n is constant, so its derivative is 0, and log sin theta has derivative cos n theta divided by sin n theta into derivative of n theta, that's equal to n. So this gives 1 by r dr by d theta is equal to cot n theta. but we need to evaluate r d theta by dr. So we can first write this gives dr by d theta is equal to r into cot n theta. So we can say this implies d theta by dr, taking the reciprocal on both sides. This is 1 divided by r cot n theta. So hence we can evaluate find the value of r d theta by dr. So this implies r d theta by dr. This is equal to r divided by r cot n theta. So this finally implies r d theta by dr. This is equal to 1 by cot n theta, which we know is equal to tan n theta. So hence we have obtained the value of r d theta by dr. So thus this tan phi 1, which is the angle between the radius vector and tangent to the first curve. So tan phi 1 will be equal to r d theta by dr, but we have computed this is equal to n theta. Now considering tan on both sides, so this implies phi 1 is equal to n theta. So this is the angle between the radius vector and the tangent vector to the first one. Now similarly consider the curve r power n is equal to b power n and cos n theta. Then apply log on both sides. We obtain, now again as in the previous case, we will get n log r is equal to log of b power n plus log of cos n theta. Now differentiate both sides with respect to theta. We obtain, now as in the previous case again, the derivative of n by r is equal to n log r n by r dr by d theta, and on the right hand side we obtain 2n sin n, because derivative of divided by cos n theta. The derivative of log is equal to 1 by cos, then derivative of cos n theta is equal to minus sin n theta. So this should be equal to minus 2n sin n theta by cos n theta. Now considering n on both sides, this implies 1 divided by r dr by d theta. This is equal to minus sin by cos is equal to minus tan theta. So this implies dr by d theta is equal to minus r tan n theta. Now taking the reciprocal, this implies d theta by dr is equal to minus 1 divided by r tan n theta. Therefore we can compute, so this implies r d theta by dr. Therefore this is equal to minus r divided by r tan n theta, now which we can write as minus 1 divided by tan n theta, and this is equal to minus cot n theta. But we know that cot n theta is equal to tan n theta plus pi by 2, or we can also write tan n theta minus pi by 2. So this implies this tan phi 2, which we can define as r d theta by dr for the second curve, and this is now computed to be equal to tan n theta plus pi by 2. Now applying tan inverse on both sides, we can see this phi 2 is equal to n theta plus pi by 2. So therefore the angle between the radius vector and the tangent vector of the second curve is phi 2. So we have computed the angle between the radius vector and tangent vector for both the curves. Hence we are ready to compute the angle of intersection. Hence the angle of intersection is, which will denote the alpha as modulus of phi 1 minus phi 2. So therefore this is equal, now phi 1 we have already computed that to be equal to n theta, then minus phi 2, which is n theta plus pi by 2. Now simplifying this, we get minus pi by 2 in the modulus, which we can write to be equal to pi by 2. So that means the angle between the radius vector and the tangent vector of the two curves were n theta and n theta plus pi by 2, which differed by a constant pi by 2 only. So the angle of intersection is phi 1 minus phi 2, which is equal to pi by 2. So the angle of intersection between the two curves is pi by 2, hence the curves are orthogonal. Now finally here we leave few exercises for the practice purpose. So these are the three exercises where we need to find the angle of intersection between the curves. Now let's look at this figure. From this figure we shall try to understand some more related parameters that are associated with the curves that are represented in the polar coordinates. These parameters include the polar tangent, polar normal, polar subtangent, and the polar subnormal. Before writing down the derivations using which we can evaluate or using which we can see what is the length of the polar tangent or the polar subnormal or polar subtangent and polar subnormal, we should first understand what we mean by all these terms. Now, if we look at this picture, we have this red line as the graph of our equation r is equal to f of theta. Then at this point P, we have this line which we represent by PT here. It's the tangent at this point P. So this is our point P here, and PT is the tangent. Then we have this PO, which we'll call the radius vector, and then we draw this line PN, and this PN is a line which is drawn perpendicular to the tangent PT at the point P. So this line PN is actually known as the normal to the curve. So normal to the curve is actually defined as a line which is perpendicular to the tangent at a point of contact of tangent with the curve. Then finally we draw this another line which we write as TON. This line TON, it is perpendicular to the radius vector OP at the point O. Then the part of this line T of P, the part OT, is known as the polar subtangent. So this is the polar subtangent here. And the part of this line TON, which we write as O to N, this part is known as the polar subnormal, which is ON. So now let's evaluate all of these parameters one by one. So first of all, we write down the polar tangent. We can see the polar tangent in this figure is this is PT. So PT is the polar tangent. We have evaluated what is the length of this PT. Now if we again look at this figure, we have this angle here. This is the angle between the radius vector and the tangent, and we know already how we calculate this angle. Then in the same figure, this angle will also be equal to the same height. Now again coming to the definition of polar tangent, the polar tangent here is equal to PT, and we will evaluate the length of this polar tangent using the right angle triangle POT. Now in this right angle triangle POT, we can write this PT as equal to PT divided by R into R, where R is this length of the radius vector. Now if we look into this triangle POT, PT is the hypotenuse of this triangle and R is the base. And we know hypotenuse of the base is equal to sec of the angle. So this is equal to R sec phi. But we know how to write down this sec phi in terms of tan. So this is equal to R square root of 1 plus tan square of phi. So this is the formula for evaluating the length of the polar subtangent. And this tan phi is the angle between the radius vector and the tangent vector, and we already have the formula for that thing, so we can represent it also in this way: r into 1 plus r d theta by dr whole square. So this is also the formula for evaluating the polar tangent. Now on similar lines we can evaluate the polar normal as well. In the above figure, the polar normal is Pn. So Pn is the polar normal, and for evaluating the formula for this polar normal, we shall consider the right angle triangle PON. So then in PON, Pn is the hypotenuse, this phi is the angle here between Pn and ON. So ON is the base and OP is the perpendicular. So we can write down this Pn here as Pn divided by R into R. Now Pn is the hypotenuse and R is the perpendicular of this triangle PN. So we got the formula hypotenuse divided by perpendicular. So hypotenuse by perpendicular, we know that is equal to sec phi, cosec phi. So this is equal to R cosec phi. And we already have the value for cosec phi in terms of cot square. So this is equal to 1 plus cot square phi. And then we have this tan phi, which is equal to r d theta by dr. So cot phi will be its reciprocal, so we can write this in this way. This is 1 plus 1 divided by r square dr by d theta whole square. So this is how do we evaluate the polar normal. On similar lines, we can also evaluate the polar subtangent. And polar subtangent here again in this triangle TOP, which is right angled at O, with the angle phi here. Then this OT is the polar subtangent. This can similarly be evaluated. This is equal to, like this was OT. This is equal to r square d theta by dr. And similarly, the polar subnormal. Now, in the above figure, this polar subnormal is actually ON. So this ON, this is also given by dr by dt. Now, let's take one example in evaluating these parameters for a given curve in parametric in polar form. Okay, so this is our example. We need to find the lengths of the polar tangent, polar normal, polar subtangent, and polar subnormal for these two curves. The first one is r is equal to a sine 2 theta and theta equal to 5 by 6. So let's take up the solution of the first one, given r is equal to a sine 2 theta. Now first of all, we shall evaluate the angle between the radius vector and the tangent. So then, taking the derivative on both sides, we get dr by d theta is equal to 2a cos 2 theta. So this implies d theta by dr is equal to 1 divided by 2a cos 2 theta. So thus this r d theta by dr, which is now equal to r divided by 2a cos 2 theta, which we can write as, now r we know it is equal to a sine 2 theta, so this is equal to a sine 2 theta whole divided by 2a cos 2 theta. Now this finally becomes 1 divided by 2 tan 2 theta. So hence, but we know that this r dr d theta by dr is equal to tan phi. So hence this angle between radius vector and tangent is, which we denote by tan phi, this is equal to 1 divided by 2 tan 2 theta. Now we have to evaluate this tan phi at theta equal to pi by 6. So this is equal to 1 divided by 2 tan 2 into pi by 6. So this is equal to 1 divided by 2 tan pi by 3. Now we know that tan pi by 3 is equal to root 3. So this is root 3 divided by 2. Now we can evaluate the values of polar tangents. So therefore polar tangent is equal to, which we denote by, this is equal to r square root of 1 plus tan square phi. So this is equal to, now r we know this is equal to a sine 2 theta into square root of 1 plus, now tan square phi is equal to 3 divided by 4. Now here we also have used theta as pi by 6. So therefore this is equal to a sine 2 pi by 6. Since we are evaluating activity here, we are evaluating this polar tangent at pi by 6, which is given in the question, in the square root of 7 divided by 4. So this becomes a sine pi by 3 into square root of 7 divided by 4. So this is equal to, now we know that the sine pi by 3 is equal to root 3 by 2. So this is equal to a root 3 divided by 2 and the square root of 7 divided by 4. So this is the length of the polar tangent. And similarly, the polar normal is, which we know this is equal to, r times square root of 1 plus cos square phi. So therefore this is equal to, now r we know it is equal to a sine pi by 3, so this will become a square root of 3 divided by 4, or we can write it as square root of 3 by 2. Now as tan phi is equal to root 3 by 2, so cos phi will be equal to 2 by root 3. So here we can substitute 1 plus 4 divided by 3. So here we mention the reason, because cot phi is equal to 2 divided by root 3. And we know that cot and tan are the reciprocals of each other. So this is equal to a square root of 3 by 4 into square root of 7 by 3. So this is the length of the polar normal. Now polar subtangent is equal to, polar subtangent is equal to r square d theta by dr. So this r square d theta by dr. Now r square is equal to a square sine square 2 theta and d theta by dr. Now we can evaluate this, find out this d theta by dr from the above calculations. So we can here see that d theta by dr is equal to 1 divided by 2a cos 2 theta. So therefore this is equal to 1 divided by 2a cos 2 theta. Now we can further simplify this, and this becomes a divided by 2 sine 2 theta into tan 2 theta. Now at theta equal to pi by 6, so this becomes a divided by 2 sine pi by 3 into tan pi by 3. Now we know that sine pi by 3 is equal to root 3 by 2 and tan pi by 3 is equal to root 3. So this finally becomes 3a divided by 4. So this is the length of the polar subtangent. And finally the polar subnormal, which we know this is equal to dr by d theta. So this is equal to dr by d theta, and dr by d we have already calculated that to be equal to 2a cos 2 theta. Now this is equal to 2a cos 2 into pi by 3, because we are evaluating this at theta is equal to pi by 6. So we have, this is pi by 6 here. So this finally becomes 2a cos pi by 3. Now this is equal to 2a, and we know cos pi by 3 is equal to 1 by 2. So this becomes equal to a. So these are the required lengths of the polar tangent, polar normal, polar subtangent, and the polar subnormal. Now if we look at the second exercise, we have to evaluate the same parameters for the curve r is equal to a into 1 plus cos theta and theta equal to tan inverse 3 by 4. Now this will be left as an exercise, and this completes this lecture.